Hello, my name is Milenia Rojas, and today I will be talking about my past project this summer, which was on the effect of n-tolpyridinium additive deposition time on product distribution in copper-mediated CO2 reduction as part of the Peters group. So a little overview as to how my talk will go about today is I will start with an introduction as to why do we care about CO2 reduction and why we use copper electrodes. Then I will go into the background and go over some past literature papers that the Peters group has published, continue on to my experimental procedures and setup, and then I will discuss my data and future projects that I have in mind. So, due to our dependency on fossil fuels for our main source of energy, CO2 emissions have increased at an alarming rate. Every year, new records highs of atmospheric CO2 are reported, and there seems to be no end in sight. The global challenge has been to find an effective approach to reduce CO2 emissions and stop the continuation of this trend. And according to the US Energy Information Administration, currently most of our energy consumption comes from fossil fuels. Only 12% comes from renewable energy. And a second challenge that we face is a way to decrease our energy reliance on fossil fuels and increase our use of renewable energy. Electrochemical CO2 reduction is a promising route to combine these two goals. By capturing CO2 emissions from large concentration sources such as industrial plants and powering electrolysis using renewable energy, we can create a carbon neutral circular economy that can use atmospheric CO2 to create multi-carbon products. And the reason why we care about multi-carbon products is not only do they have a higher energy content, but they also have a higher market price, making them economically viable. If you follow this dotted line in the figure that the Jaramillo group created, you can see that anything below the line would not be commercially viable because the cost of capturing CO2 would exceed the value of the products being made. But the products above the line seem to be promising. One specific product that we care about is ethylene. And today, copper electrodes are the only known transition metal to be a great heterogeneous catalyst for CO2 reduction because it can facilitate the formation of multi-carbon products by CC coupling on the surface of the electrode. But the main issue with copper is that it is not very selective because, as you can see right here, the main products being made on a bare copper electrode is hydrogen and methane, making up over 60% of the total Faradaic efficiency. Meanwhile, ethylene only makes up a little bit over 10%. But thankfully, the Peters group has done a great amount of research to optimize the selectivity of the copper electrode and found that by using N-substituted aryl pyridinium additives that are electrode deposited in situ to the copper surface has led to a great selectivity for C2+ products. This is due to the fact that these hydrophobic organic films are able to suppress HER and methane, leading to higher ethylene Faradaic efficiencies. And as you can see in this figure right here, a bare copper electrode, most of the products being made are side products, but once you use n-tolpyridinium or phenanthylinium additives, you can see that there's a great increase in ethylene production. And a recent paper that this group has published is the silver paper, in which they were able to study the mechanisms of the additive film on a silver electrode during CO2 reduction. And the reason why they use silver instead of copper is because due to the fact that silver has a much simpler product profile, since it can only really make CO, hydrogen, and formic acid, it is easier to be able to study the intrinsic and mechanistic activity that is happening due to the film, the reaction versus as if you take a look at the copper mediated CO2 reduction, you can see that there's a bunch of products making the whole study of it more complex. And in order to understand the intrinsic activity of the system, and a metric that was determined from the experimental data was the electrochemical active surface area, otherwise known as the ECSA. And the ECSA is a way to compensate for changes in morphology due to the film or different copper surface. An ideal capacitor would follow this relationship where you can find the capacitance by the current divided by the scan rate to then solve for the relative ECSA using the capacitance of the film on the copper electrode divided by the capacitance of the blank copper electrode. And the way they were able to solve for the capacitance is using cyclic voltammetry. They plotted the current versus the applied voltage. And if you can see, these different colors are the different scan rates. They extracted the current from the center of this voltage window and then plotted it versus the scan rate to find the slope and use that slope as the value for the double layer capacitance. And from the results using small scale deposition times, they were able to see that when they plotted the partial current density to the ACSA after a certain point, the deposition no longer had an effect on CO formation, but instead had a dramatic suppression of HER. And this became the basis of my project because we wanted to see how these results translate to copper electrodes. And our experimental setup and procedure consisted of mimicking how we would normally conduct CO2 reduction, but we modified the procedure by recording the ACSA of a blank copper electrode and then depositing a 10 millimolar solution of entyl-pyridinium. I varied deposition times ranging from 10 milliseconds to 15 minutes. And then we changed the electrolyte to a fresh batch and then recorded the film modified ECSA and then conducted CO2 reduction. And in order to calculate for the ACSA, we took values at 7 different scan rates and used a potential window from negative 0.25 volts to negative 0.45 volts, which is just enough voltage to charge the double layer capacitance without having too many side reactions happening. And we deposited the film at negative 1.1 volts versus RHE. And then similar to the silver paper, we used the different scan rates and extracted it from the center of the applied voltage window, and then plotted the current densities versus the scan rate and used this formula to find for our ACSA. And then to find the CDL value for our system, we took the average of all our blank copper electrode capacitance and found that our value for the CDL was 31 microfarads, which is comparable to the literature value, which is 29 microfarads. And when we plotted the ECSA versus the log deposition time, we found that there's a reverse relationship between deposition and ECSA. And one hypothesis to this relationship is that the longer we deposit this organic film, the thicker it becomes. And because the film is non-conductive, it's covering some active sites where the current could be flowing. And to further prove this hypothesis, we took atomic force microscope images and saw that that after 5-minute deposition, there is considerable height difference. And if we were to take the average of these heights, we would see that the film does indeed become thicker, and because there's 150 nanometer difference between a blink and a 5-minute deposition. And we wanted to continue taking a look on how our films affect our product selectivity. And we saw that after, similar to the silver paper, that after a certain deposition time, there's a plateau on the selectivity of our products. And this is important because then we know that after this point, no matter how long we try to electrodeposit the additive onto the copper, there will be no change in the selectivity of our system. But something we found interesting was that although the selectivity continues to plateau, the more the ECSA decreases, the partial current density of our products continue to increase. And this leads us to believe that even though there are less active sites, the few active sites that we do have left become more active, causing this reaction to move forward. And a few challenges that we face for running longer deposition times is that the longer we run the deposition, there's more HER happening on the copper surface, and when HER is happening on the copper surface, there's bubbling, which could lead to film delamination. So ways we could modify this project to further look at the intrinsic activities is deposit the film at negative 0.7 volts versus RHE. So most of the current will be used to reduce the additive and hopefully prevent HER. And then we would possibly get more reproducible data for longer deposition times. And to further test the relationship between deposition time and film thickness, taking more AFM pictures to be able to see the average thickness and height. And then to test kinetic studies, conduct CO2 reduction at negative 0.9 volts versus RHE, which is the kinetic region of the TOEFL plot. And that concludes the end of my summer project. But after reading various literature papers, I came up with the idea of how would incorporating silver to our copper electrodes increase this C2+ selectivity. And two papers that I want to highlight is that when you incorporate silver into copper and using bimetallics for CO2 reduction, it has been proven to increase C2+ product selectivity. And CO2 reductions conducted in alkaline pH, there is an increase in ethylene, but CO2 reductions in neutral pH, there's an increase in ethanol. And my question would be is, how does the incorporation of silver to copper electrodes affect our pyridinium additive system? And would it lead to a greater selectivity, or would it just eventually plateau as well? And lastly, I would like to thank my mentors, Madeline Hicks, Nick Watkins, Yushin Wu, and Jonas Peters for their continued support, patience, and guidance. And I would like to thank the ResNext Sustainability Institute for sponsoring me, and the Caltech SFP programs and Way Fellows for having me here. So thank you.